Hello and welcome to the Loughborough University's Institute of Advanced Studies. I am Professor Estefania Cuenca and I'm the director of the IAS, and it's my absolute pleasure to welcome Liberato and Estefania to the IAS today. Welcome to all of you in the International House full room today. It's absolutely great. Also welcome people online. As always, as probably many of you know, the International House is the place where we have the most exciting, the most creative, the most fun conversations and collaborations. This is where the conversations about things that really matter happen, and this is where kind of research ideas really flow. And today we're going to talk about sustainability, which I think all of us kind of understand in very different ways, and today will be one way of looking at sustainability. As always, we run the seminar in a hybrid manner. So for those of you who are online, please post your questions. We will be monitoring them, and I'm pretty sure we will have about 10 minutes maybe in the end to ask our guests questions. For those of you in the room, please also ask questions and comments after the presentation. And you will also have an opportunity to talk during the lunch. So, you know, if you want to have a slightly longer discussion, then there will be a place for that. The presentation will be released on our YouTube channel soon after it's been presented, and we will also release it as a podcast, but we're only releasing the presentations and not the Q&A, so there is space for debate. Without any further ado, I would like to pass over to Anna Blanco to introduce our guest today.
Yes, so I want to thank you all for coming. It was a very busy schedule today in our school, so thank you for making the time. I want to thank the IIS for the funding and the support staff for helping with all the arrangements and for this session and the visit in general. I'm particularly pleased to introduce these IIS fellows, Professor Liberato Ferrara and Dr. Estefania Cuenca Asensio, Chair and Assistant Professor of Structural Analysis and Design in Politecnico di Milano. I'm very excited because I've followed their work for a long time. But when I reference Liberato's work in my PhD thesis, so that's how long. And also with Estefania, who I believe we have followed parallel paths with similar origins back in Spain, similar topics, and then moving on to develop our careers abroad. They're very active at the European level research funding. Liberato was chair for the Horizon 2020 project Resilience. So that's rethinking coastal defense and green energy service infrastructures through enhanced durability, high performance cement-based materials. Also smart things. I don't know if you're familiar with that. That's a role of another very, very strong, very interesting project around new life cycle thinking and durability-based approaches for the design of concrete structures with self-healing, repair, mortar, and grouts as technologies. And this is a collaboration with multiple institutions. There were also partners in the EU cost action, SARCOS on self-healing as preventive repair of concrete structure. We included an interlaboratory testing activity, so that we were invited to participate and culminated sort of in a joint publication with multiple institutions. So we're very proud of that. And so that was our most recent collaboration. And now we're exploring what options we have to establish a more consolidated ways to collaborate around cementitious composites and innovative production methods. So thank you very much again for coming today.
Okay. Thank you, Xenia, for nice welcome. Thank you, Anna, for the introduction, and also for having organized and managed this visit of ours. I'm really very, very happy, and thank you all for coming to be here and share the ideas of the work that we have been doing. As you can see, we named ourselves the Resilience after the name that we gave to one of our Horizon 2020 projects. And I'm going to share with you some of the work that we have been doing, starting from this here. As a matter of fact, I think a couple of months ago, I was in Brussels, and you know, the Schtroumpfs, they come from Belgium. People of my generation, we grow up with these cartoons, and they, you know, made up the Sustainable Development Goal of the United Nations with these funny characters. There was this study in 2015 which tried to assess which was the progress since these Sustainable Development Goals were assessed up to then, and you can see that, you know, we're quite struggling with them. But the message that I start from, the picture there is the Museum of Tomorrow in Rio de Janeiro, in the harbor of Rio de Janeiro, Museu do Amanhã. I hope that my Portuguese is tolerable. And when I visited it, it was 2018 in the well, in our summer, it was their winter. I was hit by a message which was there, which is this one. We have become a geological force. You know, for us in civil engineering, when we speak about geological accidents like landslides, floods, and so on, we think of this. But as a matter of fact, now mankind has become so powerful that we shape the planet, basically. And what is, at least this is my point of view, what is the most, powerful driving force that we have is the fact that we relocate, we migrate, to use the word that you like, most of all from the countryside to the urban areas. And this means that we will require buildings for dwellings, we will require infrastructures for transportation, for moving, and any kind of structure and infrastructure that we need for our daily life. And as a matter of fact, this started quite some time ago. This is the road network at the time of the Roman Empire, the time of the maximum expansion of the Roman Empire during the empires of Trajan and Adrian in the 2nd century after Christ. And last year in New York Times, there was this picture. This is a highway junction in Houston, Texas. And this is Siena, a medieval town in Italy. The picture around the same scale. So Siena fits in that same space. Transportation is a big issue. We do not realize, or at least we did not realize how important it is until we were stuck. We were forced to stay at home, and during the pandemics, or when the Suez Canal was blocked by a ship. And I remember in Italian newspapers, it was written, this year at Christmas, no toys because the ships are blocked in the Suez Canal, and all the toys came through that channel. So this is really something important. Why did I add the Pantheon? Just not to match with the Roman thing. The Pantheon, I always use this picture to address one concept, because when sad accidents happen, we read, oh, the Romans were able to do concrete very well because look at the structures, the Roman bridges, the Romans, so on. But I used to say this because does not exist the concept of durability of a material. We use a material to make a structure. So the durability makes sense only if you think of the material in the structure and where the structure is. The Pantheon is in a urban area with almost no traffic, it's pedestrian now. The sea is 20, 30 kilometers away, so it's not that close. But most of all, this structure is massive, works in compression. The level of stress that concrete withstands is negligible. There is no reinforcement. So you have to think of all of these things when you think of the durability of a material. It's a fantastic structure because there is a strong engineering concept, but for the fact that the dome starts here, but you have this wall up to here, and this is exactly the point where the hoop stresses change from tensile to compressive. So when they are compressive, concrete works well. You don't need confinement. When they are tensile, you need confinement. So it's amazing that the Romans had an intuit about this. But anyway, so in this context, just to say that whatever the message it is, we cannot avoid concrete. Concrete is a fantastic building material. Our need for concrete means that we need to quarry, we need to produce a lot of raw materials, we need to produce cement, and this is a process which impacts our. But really, we should not believe that we can have an alternative, a real alternative to concrete. Our colleague, Karen Scrivener from EPFL, made the study and realized that if we would like to replace all what we do with concrete with timber, we will need a forestry surface like one of India every year, which means that we need to replace it. And the other thing is, sadly, the fires in LA demonstrated that concrete can survive fire. Timber is a different thing. You can design timber structure so that people survive and can escape from that. But after that, the building itself become part of the fire load. And but about concrete, there is a misperception, in my opinion, because we know that concrete is made of cement and cement impacts and so on. But there was a study. This study is not very new. It's 15 years old, by a Brazilian group. And they put the compressive strength versus the binder consumption. It's well known that to have a better concrete in terms of strength, you need to put more binder into that, more cement. And the conclusion at this point will be, okay, a better concrete will be more impactful. So let's build with a less powerful, less strong concrete. But the issue is that this is not the right unit to look. The metric does matter. Look at how much strength can you extract from the unit content of binder. If you look at the content of binder per unit strength, you see that the trend is completely opposite. So using a better concrete is better, provided that you know how to use it and how to design with it. So the strategies are there. We can reduce CO2 from clinker production. Surely I would not say that we have to stick to the way we do things now. We can always improve. We can use cements which contain less clinker, but there will be some problems, as we will see, which we are here to solve. We are researchers, so that is our job. We can reduce cement in concrete. We can make concrete with lower cement content. But most of all, if we are going to use concrete with a higher strength, we can reduce the amount of concrete that we use in our structure for the same performance or for even better performance. So this is the context in which we started. These are the topics which I will go through. So advanced cement-bearing materials, circular economy strategies, life cycle, carbon capture, 3D printing, all these you have to see as it's a word that you find nowadays in project, mutually enabling technologies. 3D printing, in my opinion, cannot exist if you do not use advanced cement-based materials or advanced structural concept, because at a certain point, you will reach the asymptote of each other. Or carbon capture is another aspect that you can improve if you use better concretes and so on. So we try to, frame this into a isolation of that. We started with this idea in mind with the resilience project, and we said we want to access product, process, content. Product is UHPC, is well known on the market, and it's advertised for its high compressive strength. At a certain point, I say, from a structural engineering perspective, this higher compressive strength becomes useless because you cannot squeeze the sides of your columns below a certain limit because it's no longer a matter of strength, it becomes a matter of stiffness and buckling. And the two properties are not proportional. So what you look from UHPC is not only strength, it's toughness. And you have to upgrade this to the process. The other movie was when we casted half a cubic meter UHPC on a real job site with a very, basically skilled workers, because that is the way to go. Construction industry is made of, medium to low skilled workers. So you need to upgrade their skills if you want to really make the innovation breakthrough. But what we wanted to look into, and Anna, mentioned it in the introduction, is the self-filling capacity. This is how these materials, because of their composition, because of their engineering mix design, are able to self-fill the cracks, provided that they are in good environment, which means that there has to be some moisture, basically. So this was what we looked into, and this is what we proved in a job site. This was one of the pilots in our resilience project. Very simple one. I said it's a swimming pool. We use a geothermal water. It's not thermal. It's not a spa. It's a water which contains sulfates and chlorides, so very aggressive. But going from ordinary concrete to UHPC, we reduced the thickness from 10 centimeter. You can see inside this is about 1.5 meter wall, so not very demanding. From 10 centimeter to 3 centimeter. The other important thing is that the reduction to 3 centimeter was allowed not simply because we changed the material, because if you limit to the material, you go to 6. We changed also the structural concept, not a cantilever wall, but plates connected by, we call it them buttresses, because we wanted to remind us of the Romanesque architecture, because really these slabs transmit a thrust to these columns here. So we changed the structural concept going to a slab because the slab is a redundant structure. It can redistribute stresses, it can exploit the properties of this material. So even if the mixed design, if you look at the cubic meter of this material, you have more cement than in ordinary concrete. But if you compare the square meter of a wall, you see that in this case, 1 square meter contains 35 kilos of cement. In this case, it contains only 18. And even if you add slag, which is a supplementary cementitious material, the sum is still lower than that. So this is the way to look at the use of ultra high performance construction material, whatever they are. So, okay. The other thing is, okay, we have these materials, but we need to know how to design with them. There are guidelines in the International Design Code nowadays, but when it comes to durability, the codes are a little bit lazy on this. The codes on durability are prescriptive. They simply recommend a minimum cement content, the maximum water cement ratio, and ultra high performance material automatically satisfy this. So how can you compare the benefits if they are all above the threshold? So we developed the methodology. In this sense, the multidisciplinarity was quite nice because we were discussing with people in timber design, and we were discussing about fire design. When you design for fire a timber structure, you calculate the time and you calculate how much thickness of timber is burned in that time, and you remove that thickness from the cross section. So we said, let's do exactly the same. If the chlorides penetrate, let's remove from the cross section, which is a little bit harsh because then we went and we tested the materials. But what we wanted to demonstrate with that is that due to that reduction in volume, the costs of constructing a structure, construction costs, which are up to here, orange, green, and yellow. Construction costs in ordinary reinforced concrete or in UAPC are exactly more or less the same. So this is important. This is important when you go to real industrial application. You cannot say, oh, we'll save money in 50 years from now. No, the return on investment must be reasonable. Otherwise, the innovation will not go to the market. So in that case, we managed with the design to have the same construction cost, and you greatly save on the maintenance because of the higher durability and less maintenance. How can you predict the maintenance? This was the other issue. Most of all, because you use UAPC almost in most cases without ordinary reinforcement. So if you think of the model for corrosion, you do not have a bar which corrodes there, so you cannot apply this model. So we investigated the long-term performance with experiments and modeling. I will not go into the details. We used also a little bit of AI to reshuffle things because we had a good database of about, I think, more than 750 cracks that we could scan. So it was a good database to train our own model. The paper was just published yesterday. Our student was very, very happy about that. So we developed a crack closure law, and we used this in the models, and we were able, through the evolution of the performance over time, to track the maintenance. So, for example, for the model for the structure with the slab supported by columns, if we used our approach, we had no maintenance or a maximum of 3 maintenance compared to 10 to 15 in ordinary reinforced concrete structure. So this was the methodology that we developed to calculate the cost. And then we went further. For example, we investigated how these properties apply to impact, if you want to use for protective structures, how the material is able to recover its properties, how these materials survive higher temperature. This is particularly important if you go to nuclear contain the secondary vessels, which can be subjected to up to 300 degrees constant temperature. It's high, but not extremely high. So the material still keeps its performance. We heated the material up to 200 degrees, these ones here, and we exposed it to high temperature. And after curing them for 3 months, the material was able to close back the crack. So it's able to survive with this activity. We investigated also freeze and thaw as well, and we try to come up with the design matrix to address the choice of the best material for the best application. Ending up, I spoke about nuclear, so the transition towards the energy world was a little bit natural. And we look at into, this is the, well, this was still the European Union with 28 countries. So this survey was before Brexit. This is the energy mix for all the European countries. So we still dependent, it's some years ago, we still depend on 10% on coal, but there are countries like Estonia, Poland, which depends on 40–50% on coal. So how the advanced materials can help into the energy transition? So we look at into energy harvesting, for example. This is the structure. We collaborated with this company. This is they go into gravity energy storage. So they lift up masses, they transform the electric energy into potential energy when there is a surplus, and they release it when there is the demand. You need to have these very high, up to 200-meter high frames. So the cost of this structure has a great impact on the profitability of the energy harvesting. So they ended up with this design here, which can only be made possible with fiber reinforced concrete, actually, because you can see here, you just have four regular bars, and some stirrups also here where the columns will be supported. Without fiber reinforced concrete, you cannot make this possible. You cannot have this design, and the fiber take up 50% of the total capacity of all. But obviously, in this case, you also need to go with fatigue. You need to understand how these materials behave in fatigue. So you see, we made some fatigue testing of the fiber reinforced concrete, because another application are the wind towers. If you want to go higher to harvest better energy from wind, the problem becomes frequency dominated. So you have to uncouple the eigenfrequency of the rotor from the eigenfrequency of the structure. And concrete structure is a good solution for this. So for this reason, we have also studied how this material can recover their natural frequency, their stiffness, and we are going to start in a couple of months. Marie Curie fellow will come to Politecnico just to study these things. Another thing was circular economy. I will not go deeply into that because Estefania will talk of this, but we investigated our project. We said was a joke. We said we are a zero waste project. So we recycled all our specimens. We made new UHPC, and we demonstrated that it's possible to keep the performance, to keep the self-filling capacity, and if you have the possibility to recover the fines, also to reduce the amount of cement that you put in the new concrete. But still related to energy, if you are going to abandon coal, we are going to miss an important constituent of advanced concrete, which is called fly ashes. So we have to find alternative fly ashes sources. Nowadays, steel is no longer produced from blast furnaces. We produce from electric arc furnaces, and the slags are different. So are those slags equally good to be used in concrete? So we have started this project with the company. They work with municipal solid waste incinerator ashes, and they use them also as carbon sinking. And the issue is that the properties, you need to adjust the properties because they can be different from conventional, traditional coal fly ashes that we are used to nowadays. And this also was dictated by, probably Estefania will speak about that. What does energy transition mean? We were in this project funded by the Research Fund for Coal and Steel. They were Polish partners and also UK partners, University of Warwick, University of Exeter. If we close the coal mine, what does it mean? It means that we have to handle a waste stock like that. That is a mine in near Katowice in Poland. What do we do with that material? And there is also the handling of the subterranean cavities, because you cannot simply close the jar and go away and forget about it. If you don't use it, you need monitoring, Wi-Fi connection to transmit the wireless sensor that transmit the information and so on. So we try to recover these wastes. There are problems in handling those wastes. They are naturally occurring radioactive materials, so you have to understand how to handle them, how can you recover them. But we realized that if you lightly cement them first, and then crush this mixture and use as aggregates in concrete or in road bases and so on, they give you a good performance. So this was a possibility that we have. Another project we are involved with is with this company, Siemens, which is partially funding a PhD position, the carbonation of the slurry because it's a way in which you can control really the carbon dioxide that you inject and they remain fixed, because in most of the processes that are nowadays advertised, you know what you pump in, but you don't know what does it goes out. If you have sparkling water and you slightly agitate it and you release the the bottle, your carbon dioxide goes away. I always do that because I don't like too much sparkling water, so I want some carbon dioxide to do that. And then we also went into 3D printing. Our early attempts were obviously a little bit of develop a particle finite element based scopes to model and design the engineering printing process. And finally, we were able also to set up our own 3D printing lab. First nucleus was a robot, but we kept on developing our 3D printing tools. So nowadays we are able to simulate the printing of complex objects and the piling up of the layers. From that knowledge, the knowledge of 3D printing material, which must exhibit fast setting, we went into this project. So the mix is like a 3D printing mix. It sets almost immediately, a little bit less than 3D printing one, but this was used for tunnel retrofitting. There is this slip forming unit. You pump at time zero a self-compacting fiber reinforced concrete mix, and after 1 hour you are able to slip form. So the valve is able to withstand and develop a compressive strength of about 8 megapascal in 1 hour in order to be able to stand that. And in order to bring this to the real application, we had to validate it with real scale testing. So these are 5-meter diameter mock-ups of tunnel valves that we tested in different load combination in the JRC lab of the European Community near Milan. We analyzed the cracking. This is only fiber reinforced concrete. And we went to a real site. This was about 150-meter tunnel on the highway. We demonstrated that using this technology, we saved 2 months on the construction site time. The material was not so, dramatically different in terms of impact, because you see, if you compare the global warming potential of these materials, this one, and you sum up concrete and steel in the classic solution, you have a saving which is about 5%. And sometimes if you go for 5% saving, you say, oh, is really worthwhile all this complicated process. What was interesting was that over 8 months, we went down to less than 7 or just 6.5. So this saving was the key driver for the innovation, because for a stakeholder, okay, you close the highways 2 months less, you keep the workers 2 months less on the road, you avoid 2 months of vehicles in the queue and so on. And nowadays, what we are trying to understand, can we correlate to the rate of fatal accidents that are on a highway because of the reduced construction site? So the social impact of the innovation in material and in structural engineering. These are the last slides. We apply these materials also to structural retrofitting. This is another pilot of the Resilient project in Malta. It's a water tower in the abattoir area. This was the situation when we picked it up and decided to, put in the project, and this is how it is now, and is listed now in, the historical artifacts in Malta. We are trying from that experience now to embed in our retrofitting material self-sensing capability, so providing some conductivity to the material so that material itself becomes a sensor. And we are now going, I remember that, going to produce these materials, these UHPC, using SEM4, using natural pozzolana, using amorphous alloy fiber, so trying to go lower on the embedded carbon footprint from the material, and try to incorporate phase-changing materials. We want to use this in the retrofitting. This is a fantastic site in the Czech Republic. Ostrava was the oldest blast furnace in the Habsburg Empire, and it produced steel for the Trieste naval yards. So the story is fantastic. There are some buildings which date back to the early 90s, which are in concrete, that we want to retrofit, and we are going to test them in these houses. These are in Madrid from one of the partners of the project. So we want to, mix up the concept into that, and the movies from the first experiments that our students did in the lab. Going to retrofitting and to new material, I think this is the very last slide, or more or less there. We had a case study. This is a water treatment plant in Genoa. It's located here. The airport is here, and this was a former steel factory now abandoned. So the environment is close to the sea. There is acid attack from the environment. So it's a multi-attack exposure site. We use advanced materials for the design of this water treatment plant. You can see there a structural model. But what we wanted to understand, if we use better materials for this structure, which has a longer durability then, and we try to predict how the durability changes the structural performance, how this structure will respond to an accident like an earthquake with a certain return period, and what does this better performance means in terms of the survival capacity of the structure, and then, and this is the point where we are now, how does this impact the promptness of recovery to the disaster of the whole community? Because this is a water treatment plant, so it will affect the possibility for a community which is hit by the disaster to have this essential service. Well, this is all on the technical part. There is also the social part. We went to the first new European Bauhaus fair some years ago in Brussels to showcase some of our innovations, and we organized, these are some pictures of the World Research Group at the last Rilem Spring conference that we held in Milano in the former stock exchange place. These are some pictures from the project meetings that we had in the past in Valencia, Milan, that was Athens, I think that was Paris there. And yeah, obviously we are in academia, we have to train students, and these are the master students who worked with us over the past years, who shared the enthusiasm on research, and this is our research group, Italia. Some of my daughters are there simply during the dinner of the last conference, and really acknowledge Stefania, who will talk later with Francesco, is part of the stronghold of the research group and made possible having these fantastic people working with us, and acknowledge obviously as well also the funding bodies for this research, and thank you all for the attention. Or probably Stefania can. Okay.
Okay, so good morning, everybody. Thank you, Anna, for the presentation. Thank you, Shania, also for the introduction. I also want to say thank you to the Institute of Advanced Studies for the funding this week, and for sure also for the invitation. Thank you. So, thank you also for your time to be here today. So, okay, Liberato explains very well, also give you a panoramic view of all the research that we are performing in Politecnico di Milano. But now I want to focus more on the concrete recycling and so on, always in the framework of sustainability. So, okay, great. Okay. So this is the framework in which I want to explain you today that, okay, as Liberato said, we need concrete for constructions because after water is the most used material in the world. So and also as he explained, to replace with timber is not so convenient. So we need cement. So we need to focus or to concentrate to how to use cement or concrete, but in a sustainable way. So what we can do it, for example, in a framework of circular economy, we have worked with these projects with resilience, Sensier and Mill Rescue. So we can recycle and reuse. So we have cement and we produce concrete, and then with concrete, we can use or get aggregates from this concrete, or also we can reuse to produce cement with this kind of concrete, crushing the concrete and proceeding with the sieve and so on. So let me explain you a couple of experience in terms of that. So, well, we started with a project, the European project Resilience, producing an ultra-high fibrous concrete that is a ultra-high performance concrete that obviously, as you can see here, we with the reference mix, the quantity of the amount of cement is really high. But in terms of sustainability, we are using a less volume of concrete. So it's interesting in this side. Well, we have produced several kinds of mixes, as you can see, the 50 and 100. And what does it mean? Is that we have produced then a kind of concretes, but replacing part of the aggregates. So, for example, in the reference mix, you can see that we have used around 800 of aggregates per cubic meter. But in this case, we have replaced half part of the aggregates with recycled aggregates. And in this case, all the quantity of aggregates have been completely replaced. But now today, I want to focus only on this because this is particularly interesting because we have two mixes and we have also reduced the quantity of cement. So in terms of sustainability, it's really interesting because we have used a lower quantity of cement. And that's interesting because here we are recycling ultra-high fibrous concrete. So our question was, okay, it's possible to produce a new ultra-high fibrous concrete, but more sustainable, or recycling the former one? Okay, so it was possible. And okay, also another thing is that not only replaces the cement, but also the aggregate. So as you can see, with the R is that it's recycled. So in the first one, we have a mix in which all the aggregates, the coarse aggregates, were completely replaced. Okay, we're talking about maybe all of you are not so familiar with ultra-high fibrous concrete. So the coarse aggregates in this kind of mixes is around 2 millimeters. So this is all 2 millimeters passed with the sieve. And in this case, we have also fines. And fines are, in this case, when the aggregates passed a sieve of around 75 microns. So it's really thin. So, okay, here you can see the mixed design of these two materials, two concretes. And here you can see better, which is the quantity of sand, the recycled aggregates, and recycled fines with reduced binder. And this is the experimental program. Okay, I'm trying to explain in a way for all those people that are not so familiar with these things. Okay, concrete has the ability to auto-repair itself, that is self-healing, and also self-healing is really interesting in terms of durability because repairing itself, the maintenance on time of the structure, concrete structure is less, so it's more sustainable in this sense. So, well, to study in this case, what we do. Well, concrete has this property to repair itself, but the thing is that, okay, we pre-crack, or in this case, we pre-crack the concrete, but we observe into views. So how concrete seal this, but only in the surface, how the crack seals, also repair, but only in the surface, by means of a microscope or digital microscope, taking pictures before and after the healing curing periods. And also we perform another test that we call sorptivity absorption test. And this is particularly interesting because it's to analyze and also allow us to quantify how the crack is cured, but also repaired, but in depth, also in the inner part, not only in the surface. So this is particularly interesting. for sure also from a mechanical point of view is particularly interesting. So, well, very, very quickly, sortivity test is an absorption test. So we subject these prismatic specimens, in this case, were 4 centimeters, 4 centimeter 60. And this is, you can see here, is the water that absorb water across the notch in this side, because this is waterproof with silicone. So it's a unidirectional flow in this sense. And we put during different cleaning periods. What is the scheme, the general scheme? Okay, this is the group 0, that is for mechanical characterization of the material. And then we have 3 paths in this case. So, because what is another important aspect is that, okay, concrete has the ability to repair itself, but once or more times, because obviously, okay, we can repair once the crack maybe, but what happened then in a long term, this is particularly interesting from the civil engineering point of view. So we have observed, or we can analyze another methodology, another process, that we pre-crack all the specimens, but with a 3-point binding test, a classical 3-point binding test, up to, in this case, 150 microns. And then we immerse the specimens in a chloride solution in order to promote also the self-healing aspect in a chloride environment. And after 1 month, we recrack again. Then after 2 months, recrack again, 3 months, recrack again, and also at 6 months. So a lot of recracking, and let's say, how does it work? So, well, with these pictures, we have used also the merging with the, okay, we take pictures with digital microscope, and we merge the images with the with Photoshop, sorry. And here you can see what is the evolution of the crack. This is completely open because it's just after pre-cracking, after 1 month and after 2 months. And then with the binarization, okay, quantifying the pixels, we have the area, the idea of the area after pre-cracking and after several healing periods. So, well, in order to assess all those things, it's important also to quantify the effects, not only in a qualitative way. So here in this graph, we have focused on those mixes, and we have designed, or we have used, calculated 2 several indexes that call index of crack sealing in order to evaluate only the surface of the crack. And as you can see here, is we have a ratio, a relationship between the area of the crack, so area just after the cracking, and also the area after several periods of healing, curing. So, well, as you can see here, is the difference is that this is only aggregates, let's say around 2 millimeters, and this is with fines. So in this case, we observe that this is quite most important, and it's usually also in self-healing that after 1 month, the behavior is almost, the level of the index of crack sealing is 0.5. So we have take into account that if the ideal situation is that the index of crack sealing is equal to 1, that is mean that the crack is completely sealed. So after only 1 month, we have repaired half of the crack. So this is quite interesting. But then in this case, we are only analyzing in this graph only pre-cracking, not recracking. So that's why it's improving a long time. So this is after 1, 3, and in this case, also, we observed that for this mix was better the behavior because after 6 months, we reach the best rate for this kind of index. And the other one was slightly better. Well, as we expected, on the right, we can see the graph of the evolution of the repeated cracking, obviously. If we are repeating this cracking process, cracking, healing, the behavior was worse. And as you can see, this is quite interesting also because here after 1 to 3, obviously is decreasing, but then we have a slight increase. Why? Why? That's obviously because we have 3 months occurring, that not so short period of cracking healing. Well, this is another perspective of the same mixes. We have the index of crack sealing compared to the crack width. Obviously, self-healing, what the behavior is better with when the crack width is very thin. And obviously the index of crack healing is lower when the crack width is higher, as expected. This in terms of sealing only in the surface, but what happens in the cracking depth regarding also the inner part of the crack, is repair or not? Okay, so the structure is the same. In the left, we are analyzing the only per-cracking, not the recracking. On the right side, we have repeated cracking, thin cracking. Well, in this case, we have analyzed it. We have calculated this kind of index dividing the sortivity. Sortivity is a rate of absorption, as I explained you with the prismatic specimens and so on. Well, so the tendency is like this, also a long time. So it's better also in this case for the case of healing without the fines. So it is due to the granulometry, the size of the fine. So it absorbs more water. So in terms of healing was also expected this kind of behavior. But what happens regarding healing? Regarding healing, as you can see here, after 1-2 months is more or less constant is the behavior regarding the index. But then after 6 months drops, so it's not so good after time when we repeat cracking again and again. Well, this is only we have represented the index of the sealing and this, the healing and sealing here, relating both values that I explained here. So as you can see here is a little bit more higher, and this is lower. But what happened with repeated healing? These are points randomly distributed, so there is not a clear tendency, but obviously, in this case, the healing rate constant, so it's not so good, obviously, when we are repeated or in a long time. So, okay, conclusions are more or less, I have explained it. So, okay, I think I think it's better to move to the other experience. So, another experience around recycling. So, also Liberato explained something about it. This project in which we have participated in a rescue project that is how we can use this old coal mine waste that is huge, the quantity, you know. We see a picture of the mine in Poland. So, well, in this case, I'm going to explain you this kind of this project. We obtain, we use coal mining waste from different mines, from Poltego and Marseille in Poland and Subterráneo in Spain. As you can see, this is the aspect of coal mining waste, and we produce several types of concrete, mainly two types. One type is mono-recycled concrete that we produce a concrete, in this case, not ultra high, it's an ordinary concrete, but instead to use aggregates, we use this carbon. So coal mining waste, and let's say how it works. And then we use be recycled. What's that? Because in this case, the be recycled concrete was concrete that's we use the aggregates crushing the concrete mono-recycled. So it's double recycling process. So okay, this is the mixed design. As I told you, this is an ordinary concrete. And also in another table, you can see the reference one. Okay, obviously we have all the quantity of the amount of sand and gravel. And also we have coarse only and fine and coarse. What does it mean? Is that we perform a mix with, for example, in the case of course only, that we have only replaced, we only replace the gravel, the coarse aggregate, but remains the natural one, the natural sand. In the case of fine and coarse, we replace both by natural aggregate, sand, and also gravel. Okay, these are the materials, and here on the right, you can see a cross-section of a cylinder of a mono-recycled concrete, and you can see the black ones that are the coal mine waste. Use that as aggregates. Well, in this table, you can see also the compressive strength test. Just to be familiar with the identity that we have used, M is mono-recycled, B recycled, is coarse only, this is fine and coarse, and the last letter is the provider, Voltego, Subterra from Poland or Spain. And the conclusions that we are going to analyze them, but it depends, the behavior, it depends on the providers. It depends if it's obviously mono-recycled, B-recycled, so let's move on very, very quickly. Okay, you can see here in the column provider, the rate of replacement for each mix. And as you can see in the last column, more or less the compressive strength test was pretty the same. Only in this case, we obtained the highest value for the mono-recycled course only from Subterra. And here you can see in this graph compressive strength compared to a long time. So are quite good, as I told you from the table, was the ultimate peak. But here is more or less quite good and quite, let's say, similar with obviously this passion. But the better one was this, as I told you in the last slide. But for example, in the green one, that is B recycled, double recycled course only from Subterra was a little bit worse in the early stage, but then it was increasing because maybe it's because we need more time to iterate the cement particles and so on. So then, for example, in this case, the green one was a little bit worse, but then we have a good performance after 60 days. Also, we analyzed a lot of properties. For example, just to show some of them is we test these concretes against chloride penetration. We perform cylinders and we isolate waterproof all the surface. Only the flow, the water was the chlorides for sure to simulate our marine environment was from one side. That's why it's easy also to understand then what is a flow, unidirectional flow of the water, and then with a cross section of the cylinder we can observe which is the progression of the penetration of chlorides inside to the cylinder, the specimen. So, well, as you can see, this is chloride penetration, so the better behavior in our case was double recycled. B recycled with course only from Subterra, and finally, this is in the 3 months in the early term. But then after 1 year, because we monitor during 1 year all those behavior of this kind of mixes, and after 1 year we have the best behavior for this one, be recycled, course only, and fine and course always from Subterra. Subterra, it seems that works better this in our case. Also, we perform carbonation test. As you can see, as you know, maybe concrete when it's exposed to external environment, also due to the carbon dioxide and so on, can carbonate, obviously. And here you can see the evolution about the carbonated area along the time, also up to 1 year. Well, as you can see, also the behavior was very, very promising for the be recycled final course from Subterra. So what's quite good, and we can, which is the thing is that the experience was quite good, was satisfying because it's possible to use a be recycled concrete with properties that are really interesting in terms of chlorides, compressive strength, mechanical, and so on. And it's possible to use and to produce this material, in this case, using waste, because otherwise it's a huge problem, because it's a problem to how to manage with this kind of waste. So this is our second experience. So that's all from my side. So thank you very much.